In this class, in the unit waves, we will discuss about principle of superposition, then phase and group velocities, and then dispersion. So let us start with principle of superposition. What is the idea of superposition? Suppose a large number of waves are propagating through a region. Then what is the resultant disturbance at a particular point? We know that wave motion is the propagation of a disturbance through a region. Then what is the resultant disturbance at a particular point due to this large number of waves? We can say that the resultant disturbance at any point, let us say I use the term psi for that, this is equal to the sum of the individual displacement disturbances, psi 1, psi 2, psi 3, etc. Psi 1 is the disturbance at that point due to wave 1, psi 2 is the disturbance due to wave 2 at the same point due to wave 2, psi 3 is the disturbance at the same point due to wave 3. So the resultant disturbance at any point is the sum of the individual disturbances, sum of the disturbances due to individual waves. Now this disturbance can be let us say the displacement of a stretched string from the mean position, or the displacement of a water surface. Okay, say a large number of waves are passing through a water surface. You throw some multiple stones, different number of stones on a water surface, or on the surface of a pond. Then we get different waves on the water surface. Then the resultant displacement at any point on the water surface is the displacements due to individual waves. So this psi can be the displacement of a stretched string from the mean position, displacement of water surface from the mean position. If we consider electromagnetic wave propagating through vacuum, then this psi can be the electric field, resultant electric field at any point in vacuum. So this summation, we have to take the magnitude as well as direction, because the displacement can be, the displacement due to one wave can be in the upward direction, displacement due to another wave can be in the downward direction, can be in any other direction. So we have to take the vector sum of, I have not given the vector symbol here, but we have to take the vector sum. Okay. Similarly for electric field is also a vector quantity. So in the case of electromagnetic field, electromagnetic waves, different electromagnetic waves propagating through a region, the resultant electric field at any point is the vector sum of the electric fields due to individual waves. So principle of superposition can be stated like this: when a large number of waves are propagating through a medium, the resultant disturbance at any point is the sum of the disturbances due to individual waves. We can say the sum of the disturbance due to individual waves taking into account both magnitude and direction. In other words, it is the vector sum of individual disturbances. Now let us see, let us apply this principle of superposition to two waves traveling along positive x direction. Consider, here we are going to discuss about phase and group velocities of a wave. Okay, phase velocity and group velocity. Already we have seen the term phase velocity. When a simple harmonic wave is propagating through a region, the wave velocity is usually phase velocity. What is phase velocity? It is the velocity with which constant phase of the wave propagates. A point of constant phase of the wave propagates. Okay, see, we will see what is the meaning of group velocity. So let us consider two simple harmonic waves moving along positive x direction. They have a similar, same amplitude, but slightly different wavelengths. Okay, so consider these two waves. We are considering waves moving along x direction. Okay, one dimensional waves. Amplitude is a. I am using sine function. We can use sine function or cos function. So k1x minus omega 1t. We know that when you write it like this, kx minus omega t or omega t minus kx, it represents a wave traveling along positive x direction. So what is this k1? K1 is the wave number. It is 2 pi by lambda 1. So wavelength of the first wave is lambda 1. And what is omega 1? It is the angular frequency. It is 2 pi nu 1. Okay. nu 1 is the frequency, and this nu 1 times lambda 1 is v1 velocity, phase velocity of the first wave v1, and we know that also we can write this phase velocity as omega by k. So omega 1 by k1 is v1. Correct. When you take omega 1 by k1, you automatically will get nu 1 lambda 1. So this is the first wave traveling along positive x direction with wavelength lambda. Now consider another wave having the same amplitude moving along the same direction, positive x direction, but with a slightly different wavelength. So if wavelength is different, wave number will be different, and angular frequency also will be different. So I will use k2x minus omega 2t. So okay, you can get omega 2, similar equation you can write, and omega 2 by k2 is equal to v2. So phase velocity of the first wave is omega 1 by k1, and phase velocity of the second wave is omega 2 by k2. Okay. Now let us consider the superposition between these two waves. What is the, when these two waves are traveling along positive x direction along the same region, what is the resultant displacement? It's a sum of the individual displacement. So we can write a sine. Maybe we can take this a outside, it's common, a sine k1x minus omega 1t plus sine k2x minus omega 2t. Okay, now let us try to find out this. We will use an identity here. There is a result that sine c plus sine d that you have studied in your trigonometry. Sine c plus sine d is equal to 2 sine c plus d by 2 into cos c minus d by 2. Okay. So if we use this, okay, I will write this cosine term first. So what you get, 2a is the, I will write the cosine term first. So what is this cos c minus d by 2? See, this term is in this expression, this term is c, this phase is c, k1x minus omega 1t is c, and k2x minus omega 2t is d. Okay, so what is this c plus d by 2? Sorry, first I will write c minus d by 2. So what you get is cos, okay, c minus d. So we have to take k1x minus omega 1t minus k2x minus omega 2t. So I will club the terms containing x together and terms containing t time together. Okay, so x is common, I can take it outside, t is common, I can also take it outside. So finally what we are getting is k1 minus k2 by 2 into x. This is okay, minus omega 1 minus omega 2 by 2 into t. See, this term in the square bracket, the argument or angle of the cosine term, this term, this is our c minus d by 2. Okay, you can work it out. So k1x minus omega 1t minus k2x minus omega 2t divided by 2, whole divided by 2. So in that I combine the terms containing x from here, k1x minus k2x. Okay, that will be k1 minus k2x, and the 2 in the denominator I have divided both x term and t term with 2. So we get this term, and then we have minus omega 1t here, and minus of minus, so plus plus omega 1 omega 2t here. So we get essentially minus omega 1t plus omega 2t divided by 2, and I can take a minus sign outside, so we get minus of omega 1 minus omega 2t by 2. So this is our c1 minus c2 by 2. That 2 in the denominator I have split up into both terms in the numerator, both x term and t term. Okay, this is the cosine term, cos c minus d by 2. Now let me consider the sine term. Okay, so the sine term is sine c plus d by 2. I can write this as k1 plus k2 by 2 into x minus omega 1 plus omega 2 by 2 into t. Okay. Now let us use some simplified notation. Okay, we have got this k1 minus k2 by 2. So let me write let k1 minus k2 equal to delta k, and omega 1 minus omega 2 is equal to delta omega. So these are in the cosine term, and in the sine term we have k1 plus k2 by 2 and omega 1 plus omega 2 by 2. So let me write this as k1 plus k2 by 2 as k average, and omega 1 plus omega 2 by 2 as omega average. Okay. Therefore, the resultant displacement or the resultant wave is 2a cos delta k by 2 into x minus delta omega by 2 into t, and sine k average into x. Okay, including the 2 we have defined as k1 plus k2 by 2 is defined as k average into x into omega average into k average into x minus omega average into t. This is the resultant wave we have obtained. Okay, maybe I will write this. I will give some equation numbers. This is equation 1. Individual waves let me name as equation 1 and 2. And the resultant wave that we have obtained, let us call it as equation 3. Okay. Now look at equation 3. This is our resultant wave. We have used the principle of superposition to obtain this. And here we have two oscillating terms. We have a cosine term is here, it's an oscillating term, and we have a sine term is there, it's also an oscillating term. So the resultant wave has got two oscillating parts, and here the frequency is different for these two oscillating parts. The frequency for the sine term is omega average, which is omega 1 plus omega 2 by 2. So let's assume that this omega 1 and omega 2 are very close together. So omega average is approximately same as omega 1 or omega 2. So it's a large frequency. Whereas the frequency of this cosine oscillating term, this oscillating cosine term is delta omega by 2. It's very, very small frequency. Delta omega is the frequency difference between the two waves. So it's very small. Okay. So it's a small, the frequency difference is very small. I mean delta omega is very small. So we can say that one part of the oscillating wave is oscillating rapidly with an average angular frequency of frequency. The other part is oscillating slowly with a frequency delta omega. Okay, delta omega by 2. That's the frequency. Then if we try to plot these individual waves and resultant wave, what are the initial individual waves? Y1 equal to a sine k1x minus omega t, a sine wave, and the second wave is another sine wave with slightly different frequency. But the resultant wave, if you plot, it will look like this. Okay, this is an approximate diagram of the resultant wave. Here we can see that there is a rapidly oscillating part in the resultant wave, and this is given by this sine function. Okay, this rapidly oscillating part, and the slowly oscillating part is given by the cosine function. Okay, you can see that the envelope of the resultant wave as a whole is slowly varying. Envelope, or we can say amplitude of the resultant wave is slowly varying. So varying slowly with a slow frequency. So that is this cosine part, and the rapidly oscillating part in the inside of this envelope, that is the sine part. That is given by the sine part. We can also say that see the individual waves y1 and y2. Okay, if you look at these individual waves, their amplitude is constant, a. These are constant amplitude waves, but slightly different frequencies. But look at the amplitude of the resultant wave. Okay, it is initially small here, then it increases and becomes large, and then it decreases. Again it increases and decreases. That means the amplitude of the resultant wave varies. It's not constant. If you look at the envelope of the amplitude, it slowly varies. It becomes maximum, then decreases minimum, then becomes maximum, then minimum, like that. So amplitude slowly varies. For example, this equation 3, we can interpret it like this. If you look at the term in the curly bracket, you can treat it as the amplitude of the resultant wave. So you can see that the amplitude varies with x and t, with position and time. Okay, this particular figure is a snapshot in a particular time. Resultant wave, if you take a snapshot, that means if you are keeping time constant and you are looking at only spatial variation, so we can see amplitude varies with time, and it also amplitude varies with position, and it also varies with time. At the same position, after some time the amplitude will be different. So the amplitude of the resultant wave slowly changes. So this is like an amplitude modulated wave. The original individual waves were having constant amplitude, but the resultant wave is having a modulated amplitude. Amplitude has varied. Okay. We know that now there is a rapidly oscillating part and a small slowly oscillating part. This speed of the rapidly oscillating part is called the phase velocity. Phase velocity of the resultant wave. Let me use the symbol V suffix P for phase velocity. So what is the phase velocity of the resultant wave? We know that generally phase velocity can be defined as omega, can be calculated as omega by k. Okay, so here we have omega average by k average. This is the phase velocity of the resultant wave, and this amplitude the modulated amplitude part, for this part also we can define a velocity. It is slowly varying, so that we can define a velocity. How do we calculate the velocity? Coefficient of time divided by coefficient of x. Okay, so see here it is omega by k, right? Coefficient of time divided by coefficient of x. In the same way, we can calculate the velocity of the slowly oscillating part by taking coefficient of time divided by coefficient of x. Or we can say the phase, we can keep it as constant and differentiate. Okay, and that way also we can do. So the velocity of the slowly oscillating part is called group velocity. And that is, let us use the symbol Vg for that. So what is the expression for the group velocity? Coefficient of time is delta omega by 2, coefficient of x is delta k by 2. Okay, so we get delta omega by 2 divided by delta k by 2, or delta omega by delta k, delta omega by delta k. That is the group velocity of the wave. Suppose we add more and more waves. So now here we consider only the superposition of two simple harmonic waves, y1 and y2. Suppose we consider more simple harmonic waves, y3, y4, y5, etc., with slightly different wavelengths. That means slightly different wave numbers k and slightly different angular frequencies omega. Okay, so if the k values and omega values of the individual waves becomes very close together, okay, and then if we again calculate the resultant wave, we can see that the expression for the phase velocity part will be the same, omega average by k average, where omega average is omega 1 plus omega 2 plus omega 3, etc., divided by the total number. Similarly for k average. But group velocity value, this delta omega by delta k, in the limiting case when delta omega tends to 0 and delta k tends to 0, this expression becomes a derivative, d omega by dk. Okay, so the expression for the group velocity we can write as d omega by dk, rate of change of angular frequency with respect to k. Okay, so this is the idea of if you have a resultant wave with the superposition of a large number of simple harmonic waves, it will be having a phase velocity, which is the ratio of average angular frequency by average wave number, and the group velocity will be rate of change of angular frequency with respect to wave number. This type of a resultant wave with slowly varying envelope, slowly varying resultant amplitude, or an amplitude modulated wave, this is called beats. This phenomenon is observed in the case of sound waves. It can be easily observed in the case of sound waves. when, let us say, two tuning forks with slightly different frequencies are um, vibrated together, excited together, then we can hear this slowly varying resultant wave. Its amplitude, its sound, the loudness, it increases, becomes maximum, then decreases, then increases, like that. And the frequency with which the resultant wave, the amplitude or the resultant um, pitch varies, it is equal to the difference in frequencies of the individual waves. So this phenomenon is called beats. Okay. So we have defined, using the simple model, we have defined what is the phase velocity of a resultant of a large number of waves. Phase velocity is average of angular velocity, angular frequency by the ratio of average angular frequency to average wave number. And group velocity is, phase velocity is this, and group velocity is d omega by dk. Now let us consider the idea called dispersion. Now dispersion means if the phase velocity of a wave is a function of wave number or wavelength. Okay, if the phase velocity varies with wavelength or wave number, because wave number and wavelength are connected, wave number is equal to 2 pi by lambda. So if phase velocity of a wave varies with wavelength in a medium, then such a medium is called, such a phenomenon is called dispersion, and that medium is called a dispersive medium. Okay, then we say that this is a dispersive medium. So if a wave is passing through a medium and its phase velocity varies with wavelength or equivalently wave number, then that phenomenon is called dispersion, and that medium is called dispersive medium. Let us consider an example. Glass is a dispersive medium for light or electromagnetic waves. So in the case of visible light, that is very we can easily observe this in the case of visible light. So when white light passes through a glass prism, it undergoes dispersion and we see different colors are separated. We call it a dispersion. But the mechanism of this separation is actually that the phase velocity of each color varies with its wavelength. That is idea. So glass is a dispersive medium for light. Let us see how the velocity, phase velocity varies in the case of glass. For glass, when white light passes through glass, it contains from violet to red, right? Violet has the lowest lambda, minimum lambda, and this red has maximum wavelength, 400 nanometer to 700 nanometer. That is the range of wavelength for visible light. When white light passes through glass, the phase velocity of individual colors or individual waves varies in such a way that the phase velocity is minimum for violet and maximum for red. So we can say that the phase velocity increases with the wavelength. Okay, so this is the situation. Phase velocity Vp increases with lambda. So as we move from violet to red, phase velocity increases. In other words, violet has minimum wavelength phase velocity, okay, minimum phase velocity, and red has maximum phase velocity. As wavelength increases, phase velocity increases. Then what is the consequence of this? Refractive index is defined like this. This is a measure of phase velocity of a wave. It's defined as a ratio of c by v. Okay, what is c? C is the speed of light in vacuum. Actually, it is the phase speed of light in vacuum. Okay, so it is the phase speed or phase velocity in vacuum, and the denominator v is the phase speed in the medium. Phase speed in the medium. This is the refractive index of it. This is how we define refractive index of a medium. So it means that since violet has a minimum phase speed, okay, it has maximum refractive index. So violet phase speed is minimum, okay, it means refractive index is maximum. And when you go to red, when wavelength increases, phase speed increases. So phase speed is maximum for red, but refractive index is minimum. Refractive index is the ratio of C by V. So as speed increases, refractive index decreases. So we can say that when you move from violet to red, as wavelength increases, phase speed increases, but refractive index decreases. Refractive index is maximum for violet and minimum for red. Now when a white light passes through a glass, refractive index of the glass, we can derive an expression for this, sine A plus D by 2 divided by sine A by 2. Here A is the angle of the prism. Normally for an equilateral prism, this angle is 60 degree. Okay, this is the angle of the prism. And D is angle of minimum deviation. Angle of minimum deviation. Okay, in other words, it's a measure of the deviation from the straight line. I mean, a white light is passing straight without the prism in between. But if you place the prism there, then the light will bend away. It will bend inside the prism, and when it comes out, there will be a deviation from the straight line, right? That deviation we can measure a minimum deviation angle. Let's say it's a measure of the deviation from the straight path. So we can have an expression like this. This can be derived from Snell's law. Okay, so refractive index is equal to sine A plus D by 2 by sine A by 2. So if you look at this, if refractive index is maximum, then deviation is also maximum. Okay, so in the white light, when you look at violet has phase speed minimum, refractive index maximum. Then what about deviation? So deviation is also maximum. Okay, for red, phase speed is maximum, that means the refractive index is minimum. Then from this expression, this refractive index is equal to sine A plus D by 2 by sine A by 2. D is in the numerator, so if refractive index is minimum, D is minimum. Okay, so when white light is passed through a glass prism, then deviation is maximum for violet and deviation is minimum for red. So in between, the other colors will be deviated. So this is how when white light is passed through a glass prism, different colors will be experiencing different phase speed. Okay, so their deviation will be different, so they will be separated out, and that we call dispersion. So originally the idea of dispersion is the variation of phase speed with wavelength. That's called, if the phase speed of a wave varies with wavelength in a medium, it's called dispersion. As a consequence of this, these waves are separated, or the different colors are separated in white light. Okay, and such a medium is called a dispersive medium. Glass is a dispersive medium for light. Now let us try to obtain a relationship between group velocity and phase velocity in a dispersive medium. So group velocity is equal to, we know this is the expression, d omega by dk, and the average phase velocity we can write as omega by k, or omega average by k average. For the, let us say, for the resultant light, the resultant wave, the phase velocity is omega average by k average, or we can say omega by k. Then this omega I can write as k times this average phase velocity. I can substitute that value here. So this I can write as d by dk of, instead of omega, I can substitute this k times the average phase velocity of the wave. So this is, if you expand it, we get Vp plus k times d by dk of Vp. Okay, so we have an expression like this. This is the relationship between group velocity and phase velocity of a wave in a medium. Okay, so in a dispersive medium, this last term, this dVp by dk will be non-zero in a dispersive medium. So that group velocity will be different from phase velocity. See what happens in the case of glass. For the glass, phase velocity increases with wavelength. From violet to red, phase velocity increases. Therefore, this wave number is 2 pi by lambda, reciprocal of wavelength. That means phase velocity decreases with wave number because k is reciprocal of lambda. So if phase velocity increases with wavelength, it decreases with wave number. So that means we can say for light in glass, for light waves in glass, okay, light waves passing through glass, we can conclude that this rate of change of phase velocity with k is negative. Okay, from when you move from violet to red, okay, wavelength increases but wave number decreases. Okay, wave number increases from red to violet. From red to violet, wave number increases but phase velocity decreases. So this quantity is negative. The rate of change of phase velocity with k is negative, which means group velocity is less than phase velocity. Okay, the second term will be negative. This term will be negative. So group velocity will be less than phase velocity for light waves in glass. So this is the result of dispersive media. Okay, this is the idea of dispersion. Now, what is a dispersionless media or non-dispersive media? Okay, so for a non-dispersive media, phase velocity does not change with wavelength. Okay, so we can say that for a non-dispersive medium, phase velocity does not vary with wavelength. We can say this rate of change of variation of phase velocity with wave number is 0. Then group velocity is same as phase velocity. An example is vacuum is a non-dispersive medium for electromagnetic waves. Okay, electromagnetic waves can pass through vacuum with the same speed. Here the phase velocity equal to group velocity equal to c, speed of light in vacuum. And next, another example is a gas is a non-dispersive medium for sound waves. When sound waves pass through gas or air, it acts as a non-dispersive medium, so that different frequencies in sound does not move with different velocities. Okay, otherwise we will be hearing sound when we hear sound from a certain distance away, different frequencies will reach us with the different velocities, and we will get a we will not be able to distinguish what is being said. Okay, so all the different frequencies in a normal speech or a music or in any sound, it propagates with the same speed. Okay, so that means it's a non-dispersive medium. Phase velocity does not vary with wavelength. So gas is a non-dispersive medium for sound waves. So that is the idea of phase and group velocities, and the idea of dispersive and non-dispersive medium.